Welcome. Let's play some LeetCode today. Starting with this problem to some, of course, very simple problem. Let's see if I remember how to do it. Let's warm up. Okay, given an array of integers and nums, and an integer target, return the indices of the two numbers such that they add up to target. You may assume that each input has exactly one solution. You may not use the same element twice. I know there's like an O of one way to do this. No, not O of one, O of n way. Definitely a one pass way to do this. I think what the solution is you store it in. Yeah, you store each number in like a set or something, and then you say you subtract each time as you're iterating up the array. You say, hey, do we have target minus the current number in the set? And that would be your second pair, basically. So actually it'd be stored in a map, so you can have the index as well because you're outputting the index. So I think that's pretty much the solution. So index map. How about this? We'll just call it map. Yeah, index map is maybe better. And then for const num of nums, we're going to if idx, let's see, target minus the current number in idx map, then we know that we have the complement of the current number to get to the target. So we can then output both of them. Let's change this to a I version of the array, the for loop, I mean. So it's I. And then we can just output, I don't know, it doesn't matter the order. Yeah. So just output that, idx map with target minus num. We call it the complement. And that should return the index. If it's not in the index map, then set the current number in the index map. Nums I. Maybe we'll just call it num. So I set that at the current index, and then that should, I believe, work. And is there? It's always going to be exactly one solution. You may not use the same element twice. I don't think that'll be an issue because we're going to iterate up anyways on each round. So just to review, we initialize our index map, and then we make a for loop going through each of the numbers. And we find the complement, which is the target minus the current number that we're looking at. If the complement is already in the index map, then we're all good. We return I, and then index map complement, which is the index of that complement number. So, yeah, that should give us our answer. Cool. Let's see how else I did this for remainder. Yeah, there's like a weird other way to do it. remainder map. It's kind of bizarre. I don't like that at all. I like my way, not this remainder map. I think someone on the forum discussion section had this. I'm like, oh, use a remainder map. It doesn't make any intuitive sense to me. I think this makes a lot more sense just to look for the complement and to make the complement each time, because you're going to be doing it each time anyways. So even in the remainder, you're going to be subtracting. There's no real extra work. So cool. And then let's just add the time complexity. It's going to be O of n, of course. And the space complexity. This will be probably O of n. I mean, I don't think there's... I thought there would be a way to get the space complexity lower. But you actually do have to store the little indices, or whatever you want to call them. Yeah, I mean, even here, is there any way to get it to O of 1? Let me think, actually. Is there any way? Let's see. Because you don't know if the current number is really going to be the combination without a map. You don't know if any number is a value without a map of it. I'm doing what I'm doing, I don't think. Just get another random number. You can't do like looking it up in a set, because that's going to probably use extra space. So, well, it's not going to use extra space, but it's going to... Well, I mean, let me think. No, but like, what if you use the same number twice? Because you just threw them into a set. You can't use the same element twice. Yeah, you can't use like 3 and 3. This could be a disaster. You can't just like throw them. Yeah, even if you're using a set, it's still going to be O of n space complexity. Is there any way to get O of 1 and C? James with the little Google icon. Do some. I don't want to watch a video. Recording a fucking video. Nobody got no time for that. All right, O of n, blah blah. Yeah, it seems like nobody can get it better with these nice skeleton cards there. All right. One pass hash table. They are all most definitely O of n space complexity, except the first one, which is weird force, which is O of n squared time complexity. We don't want that. So cool, we got that. Let us continue on to the next one. All right, have the function tree constructor. Array, take the array of strings stored in string array. Contain pairs of integers in the following format. 2, where I1 represents a child node in a tree, and the second integer, I2, signifies that it is the parent of I1. That's interesting. So the second one in this little array thing here, little tuple, whatever you want to call it, is the parent always, which you can see forms a upper binary tree. Your program should, in this case, return the string true, because a valid binary tree can be formed. If a proper binary tree cannot be formed with integer pairs, then return false. All the integers within the tree will be unique, which means there can only be one node in the tree given integer value. That is, I believe, the case with binary trees in general. All right. So, well, this seems hard. Well, it doesn't have to be a balanced binary tree. Nobody ever said that, I don't think. So that's helpful. One thing I'm thinking, like here, I don't like hear how they don't give you like all like the information on this code or byte thing. I wish they could say like, oh, it's always going to be the input string array or whatever. It's always going to have something. You don't know like the bounds on this, so it's kind of irritating. But I would ask that in an interview usually. So this first example they give is true. Second one is false. So I really think the only way we're going to have an issue is that somehow the child is smaller than it should be, bigger than it should be. And I mean, depends what the I think the parent is also. So this works. You don't know what is what here in terms of those pairs we're given. So this is the parent of 3. This is the parent of 1, which I mean could work. But what is the parent of? I'm starting to feel like this is going to be a graph problem. Actually, we're connecting like between whatever. It's like it says it's a tree problem, but it's not really. It's just like we're dealing with a tree here, but it's actually a graph because we need to know which is like connecting to which essentially, and if it can do it. So 12 is going to be the parent of 2. So I'm like kind of visualizing the structure of the graph. I'd probably get a piece of paper and write it down. Just write it on my notepad here. So we have 12 is the parent of 2. 2 is the parent of 3 and 1. So far, so good, but then 2 is also the parent of 5. And why is that not a balanced? Well, because you can't have, you have 2 is the parent of 5, because obviously you can only have, a parent can only have 2 children in a binary tree. So, all right. Have that down. So you right away know that it's not a binary tree if the parent has 2 children. What's another case where it wouldn't be a binary tree? If the parent has a child that is too small on one of its sides or whatever. Like if we're talking about, if say if like 12 had another parent, forget this one here. If there's like you have like 12 is a parent of 5 or something. That doesn't make sense because it already has always has a child of 2. And then on its right side, I have a child of 5, but that we can't have that on a binary tree. The right side has to be bigger. Or is this not a binary search tree? Oh, this is easy. It's not a. See, this is like if that was an interview, that'd be bad. Because okay, I didn't realize it was not a binary search tree. So that changes a lot. I think this would be a lot harder problem if it was a binary search tree problem. So really all you have to do is the only way it's not a binary tree is if each parent doesn't have 2 children, right? Or it has more than 2 children. I think a binary tree can just literally be like a very spindly tree as well. It doesn't have to be like 2 children on everything. So as long as the parent doesn't have 2 children, I think that is a binary tree. Let me look that up quickly on my notes. So I don't go down a wild goose chase here necessarily. I'd probably get some slight hints at this in an interview. Like, oh yeah, it is, blah, blah. So is a binary tree, can it be completely spindly? So I don't think the last leaves can be, not have the last parent in a binary tree, basically, if that makes sense, can have like 1 child usually. Full binary tree, 2 children on every node, except the 2 leaves. What is the definition? A tree where each node has a maximum of 2, right or left. It could be 0 or 1 children, but no more than 2 children. Yeah, that's for my notes. All right. Yeah, so I think this should work. This should be pretty easy. So we just need to know that it has only a maximum of 2 children. That's the only condition. We need to check. Check if it has a maximum of 2 children. Remember the problem more carefully the first time. So because I'm going down this binary search tree kind of goose chase there. All right. So that's why you practice. Go through each of these and essentially add. It's kind of annoying the input they're giving us, but we can just parse it out pretty easily. Go through each of those. If at any point we'll have a map that essentially shows like the count of children each parent has, and if at any point it exceeds 3, then we're returning false is the output. It's a string false, not the Boolean false. I don't know why, but say levy. I wonder if they would actually, if they switch to TypeScript, if they would actually want the Boolean. It's like so weird. Why would they say? I don't know. I'm not gonna worry about it. All right. Let's see. Let's go through the pair, const pair of string array. It's just an element in this array here. Now we got to do the fun parsing. We can split essentially. Well, first you would take off the two at the end. No, the 1 at the beginning, the 1 at the end, in terms of parentheses. And then do the fun stuff. Let's do per second. Pair slice of 1 to, what is like the, I can just do paired length minus, no, so that goes all the way to the end. We want to get 1 before the end. And slice by itself is kind of weird in that it stops right before the index that you give in the second argument there. All right, so pair length minus 1. Be mindful of time here. Let's finish this by like 11:55. All right, so we have that pair slice. And then I want to essentially split on this. Kind of complicated. I think this should work though. Sometimes they say, well, why don't you console log your thing? And why don't I? All right. Oh, LGTM looks good to me. All right. So, our first and our second. And then we just look in our map. Child count. I'll call it child map just to be more particular. Yeah. So child map first equals basically the first is the child, called child count. This first is the child. Second, it does have 1 plus plus. This is the child. If child count second greater than 2, then it's an instant false. Otherwise, if we go through all of them, it's not the case, then it shall be true. The truth shall set you free. All right. I don't even think we need to get the second or the first guy in the binary search. It doesn't really matter. It doesn't really matter what the child value is. It just matters. There might also be a problem. I mean, what are like the boundaries of this? Because we can't have a cycle either. So like say 7 is a parent of 1, that'd be really bad. But are they really going to check that? Like that would be a case where it's like, no, no good. I wish they gave more bounds on this. Or like, what if it's like we're not given anything really to indicate what these pairs really are. What if you had a detached one where it's not, the whole thing isn't really detached, and you know, if you had like a 5 pointing to a 3 out here, then these are like completely detached, and it's like crazy. I mean, how much do you really want us to check here? Like a question. In an interview, they would respond, but of course, now I'm just talking to a screen here with just a vague question. I1 represents a child node and free. Second integer, parent of I1. Okay, so where I1 represents a child node in a tree. I mean, this false tree they gave us here, that's still a tree. It's just not a binary tree because 2 has 3 children. So if they're saying that it's a node in a tree, then okay, I'll take their word on it. That's not going to be a cycle or a graph or some weird other data structure. Okay, turns true. I mean, that should. No, this is a mess. This doesn't do anything. Um, so we should have. If it doesn't exist, then we can just. If it does exist, we can just iterate. Otherwise, we can set it to 1. Should work. Okay. Cool. Hides the fucking. Ah, I swear. Hides the test cases. That's so irritating. But maybe we should ask ChatGPT. It works. This is good. Or you can just view the solution. I don't know, like, the extent. The one thing I was worried about was like if it's not a tree, but I think otherwise it should do pretty good. I don't know why it wouldn't. These are kind of gross. What are you doing with this regex? This is bizarre. What are you doing, folks? Do I have to sign up to submit? Create an account. Well, I mean, I might have did it wrong if they're looking at random things. Nodes can't have multiple parents. Oh, see if parent has 2 children already. Fill in empty spaces. If not. Yeah, this is the problem of not showing the hidden test cases. All right. Well, I'm going.